Hi, how we doing, everyone? Doing good? Feeling alive? Feeling great? It's almost Thanksgiving, eh? Perfect. So, today we will finally start the final big topic of 360, and that is the Z transform. So, if everyone remembered Laplace transform, I'll try to show everyone. So, remember with Laplace transform, where you had some, I don't know, L of S, right? And then you had, like, I don't know, some poles and maybe a zero somewhere there, right? Remember that stuff? So, I don't know if he mentioned or talked about this in class, and I think he didn't, but there's a special relationship between the Laplace transform, which is for analog signals, and then the Z transform is a special case for digital systems, so digital signals. Okay, so there's one technique. I don't know if he showed it in class. I think he did, but I don't know. There's like a couple theorems. So you see this Laplace transform, right? And then you have this, I'm going to color it like this. I'm going to color this side like this, right? Here's the left side, left-hand plane, right? And then I'm going to color this side. Let's color it blue, I guess. Right-hand plane, right? So there's a cool thing that we can look at this plot with and transform it into a Z transform. So I'm going to go really, really practical with this. So point is, suppose you had this point. Let me see if I had a couple more pencils. Aha. Let's use this. So let's say I get this point right here, and this is like at infinity, and this point right here, which is at minus infinity, right? So what we're going to do is we're going to grab these points that are infinity, and then we're going to try and put them together like in a circle. So what we're going to do is we're going to pull this and then just pull it on like this. So you're going to get the following. So if you were to like take everything in this red side, and then here's this blue side, right? And if we wanted to do some like pseudo transform, we're going to get the following where, let me draw it like this. Let me see if this is going to make any sense. Z. Hold up, I'm trying to think about it. So we grab this. We're grabbing this entire thing, but just memorize it like this. Okay, here's 1. Here's minus I. Here's minus 1, and no, positive I. Here's minus I, right? So this point right here is 0, right? Okay, that's 0. And that is this right here. So all this red stuff right here, if we were to put this in like some like weird big fat circle, just encompass it like this, we're going to get the following. Something like this. Okay, where all this stuff on the left side now becomes something that's, is it inside or outside? Yes, it becomes inside the circle, okay? And then everything that's on the right-hand side, right, is outside this circle, okay? So is that kind of making some clear sense? Okay, so I assume everyone here is a master of Laplace transforms. And remember when we had this Laplace domain, right? And we had a pole. Let's say we have a pole here, right? We have a pole on the right-hand side, right? What does that mean for our system if we were to draw like a region of convergence? If we were to make it a right-sided function, it's going to be unstable, right? Only if it's left-handed. So that means if we were to, so this system, if we wanted a right-sided function, this is unstable. Having a pole on the right-hand side of the Laplace domain is going to make it unstable, okay, right? So it's on this blue area, right? On the right-hand side, right? So if we can model this, we can maybe put it right here, right? And what I'm trying to say is, if you have a pole outside this, like on the right-hand side of this Laplace domain, it's unstable. If you have a pole outside this unit circle, it's unstable if it's a right-sided function. Now, what if I had a pole, I'm starting to run out of markers, like on the inside. I'm just going to draw the pole like right here, right? It's on the left side, right? So if it's on the left side, that means it's stable. It's going to be stable and causal, which is really good. We like that. So that means if this is on the right inside this red zone, we're going to see this pole somewhere like, I guess, right here. So what I'm trying to say is, if you have poles inside this unit circle, so if the pole's in here, here, anywhere, if it's inside, you're always going to have a stable and causal system. Okay? That's the one thing I want to get to everyone's mind. So. If it's outside, okay, I know what you're talking about. So suppose you wanted a stable system with this pole, right? It's outside the unit circle. The only way for this to be stable is if it includes this unit circle. So what okay, so there's a remember this imaginary axis, right? And we wanted our region of convergence, if it were like this, right? We wanted to include that imaginary circle, imaginary line, right? So the region of convergence includes this line. So same thing with this, where we're going to draw a region of convergence for this pole, and we want to include this line. So that means instead of it going to the right side, to make it stable, we need to include this. So we would have to like draw some like big donut like this. This is probably like at I don't know, let's call it a P1 or something, and then this right here is minus P1, right? And it's gonna have a circumference of P1, right? So if we were to draw the region of convergence, it's gonna go inside to include this circle. It's gonna be stable, but it's not gonna be causal. It's gonna be stable and causal, okay? Because it's a left-sided function. All right? Actually, if you wanted me to do something for you, okay, we're gonna jump the gun on this one. So let's say, remember how we were doing these pole analysis for the Laplace transform, and we were doing something like oh, you see here, this is a pole right here, PT or something like that, PT, positive or something like that, where if we wanted to do the inverse Laplace transform, you're gonna get some A e to the p t, right? That's how we were doing this like inverse Laplace transform, right? So the same thing applies to digital systems, but it's not going to be like this. It's going to be like this. So let me do this. Inverse Z transform. So what you're all going to memorize is the following. So if this had some, I think there's a residue value. So let's say like res1 or something like that. It has a pole. So there's like coefficient. A coefficient times some pole value. There's a pole. The pole value has some residue or something like that. Remember that? So what you're going to remember is here's a residue, right? Res1. But in a digital system, let's do h of n, right? You're going to have the following. P1 to the n. Okay, like that. Okay? Do I want to do that? Oh, this is bad. Okay. General. Okay. U of n. Okay, this is a general case. Is that making sense? Kind of? Okay, so this is your pole. This is your residue. And then that's just the unit step. And then this is your n right here. This is your like time. But for this system, I have to write this on another piece of paper because this is a great question for the next part of the exam. Okay. There we go. So let's do that problem. Let's just make a system. So here's our Z transform. And I like this marker. Do you like this marker? I like this marker. It's really nice. And we have a pole right here, right? So if you were on the exam and Dr. Stuberud says, determine a stable system. What does a stable system, okay, how do you make a system stable? The region of convergence includes the unit circle or the imaginary axis for the Laplace transform. But for this case, we need to include this unit circle. So what we're going to do is, if this is a radius of P1, right, then this right here is going to be the following circle like this. And then to make it stable, it's going to go inside. It's going to go to the left. It's a left-sided function. Left-sided function. Okay? So let's give it some residue value. Res is equal to, what's a favorite number?
17.
Okay? 17, okay? So if we were to do the inverse Laplace transform of this, so I don't know, Q of n, I'm just calling some function, inverse Z transform, we're going to get the following. So following the pattern that I kind of showed you from this general equation, you're going to get, here's 17, here's your res, okay? And then your pole, that's your pole, here's P1, okay? But then there's one thing you got to do. I think, actually, let me remember this. Actually, I think, is it n? I think it's n. But there's a unit step. So remember in the Laplace transform for the left-sided functions, we had to make it u of minus t so that it would be a left-sided function. It would only exist on the left side of time. So for this one, we can do u of minus n, but we're not going to include n is equal to 0. It's a weird property. I'll probably tell you about that later, or you can look at that property. But for your unit step for a left-sided function, it's going to be minus n minus 1. There you go. So you can't include the first. So when n is equal to 0, and you get u of minus 1, that's 0. So the point is, you can't include that middle point. That's z. So this is a left-sided function. So if you were to plot this, actually, there's one big mistake I'm forgetting. Remember in the Laplace transform, when you had left-sided functions, you have to change the sign. Don't forget. There we go. Does that make sense? For left-sided functions. Okay, now let's do another example on the same plot because this is nice. Let's say we have something right here, right? There. Okay, a pole that's inside the unit circle, okay? And let's call this one, I don't know, 1/2. Okay? So that's that, okay? So let's give it a residue value. What do you guys want? 2? Okay? Right? So if we were to do the inverse Laplace Z transform of this, actually before that, if we were just looking at this pole, right? How do you make this system stable? You have to include the imaginary axis, right? So if you were to draw a little circle like that, right? Then you would have to go this way to include that unit circle, okay? So it's a right-sided function. And that means it's stable and causal, okay? So if we were to go into the inverse Z transform, we're going to get the following. H of, I'm going to call it 1, n is equal to the residue value, using colors, 2, okay? And now let's draw that pole value the pole value that we get is 1 over 2, 1/2 to the n. And then because it's a causal system, u of n. All right. And now if you wanted to add these two systems together, you just do, here's q. Do you like that? Okay, h total n is going to equal h of 1 of n plus q of n. And there you go. You have your entire system. Oh, there you go. Making some sense? So, and then now that we're on that topic, what if, okay, so you know how these poles are here, right? You know these things right here, right? We have these like functions in time, right? Functions of time, right? So does anyone remember what's the z transform of something that looks like this? Okay. General z transform for something like for x is equal to res alpha n u of n. It's gonna equal okay, x of z is gonna equal this residue value res times 1 divided by 1 minus alpha of n. No, not alpha of n. It's alpha. No. Z to the minus 1. There you go. That making sense? Yeah. Okay, there you go. So minus 1. And let me just verify with my little notes that we did it right. Let me see. Yes, there you go. So what I'm going to try and tell everyone is you're going to have to memorize the following pattern. You see this alpha right there? That's your pole. Okay, that's your pole. Okay, and then here's your residue value. That's whatever coefficients there. That's how much that function weighs, or the pole weighs. Okay, and then that's your z to the minus 1. So we're dealing with z to the minus 1s for some reason. Well, that's because I guess that's how we represent delay, z to the minus 1. If you were to do the following, q of n, z to the minus 1, this is a delay, you're going to get q of n minus 1. Just delay it like that. All right? And I feel like this should be a minus. Should it be a minus? Let me see. Something's not right. No, it is a plus. Okay, it's a plus. So for this left-sided function, yeah, this is all correct. Don't forget your minus sign. Don't forget to flip this. Easy. That should be like problem 1. All right. So that's page 2. And let's start looking at this little quizzy, because I have something really prepped for everyone, and you guys are gonna like this. Let me see. All right, there it is. Let's look at it. Q10. So I ask everyone to plot in the complex domain the location of the poles and zeros for this digital system with the transfer function of h of z is equal to 1 minus z to the minus 3. So we're going to determine the frequency response, both the magnitude and the phase, and then we're going to sketch a little block diagram. And we're going to verify in MATLAB, and I have a surprise for everyone. We're going to verify this in LT-SPICE too. So this is going to be a really nice surprise, an introduction to ECG 722, mixed signal circuit design. So what I have for you is the following. H of z is equal to 1 minus z to the minus 3 divided by 1 minus z to the minus 1. So the first thing I ask, and this is probably elementary, but where are the poles and where are the zeros? So from what I can probably tell you right now is you can technically analyze it like, oh, we kind of have a pole there and we got some zeros there, right? If we just make z is equal to 1, z minus 1 is equal to 1. But easier way to do it, and actually please do, because I've had someone fail this in an interview. They're like, okay, how many poles and zeros? They got the number of poles right, they forgot the hidden zeros. And that's a surprise I'll show you. So first off, we got to convert the entire thing into, what do you call it? Into just z. So what we're going to do is we're going to multiply, let's just multiply the top and the bottom by z to the 3 and z to the 3, okay? That makes sense? Boom, boom, right? Just multiply by 1. It's going to give you z to the minus 3, oh wait, plus 3, sorry, minus 1 divided by z to the minus 3, no, to the 3, sorry, minus z squared. But this, I don't like that because I was thinking about it. Z to the 3 minus 1, z to the 2, yes, 2, z minus 1. And do you see that? We actually have 2 poles and another pole right there. Look at that. Look at this hidden pole right there. We have 2 poles that are located at 0. So what I'm going to do for you all is, if we were going to draw this, let's bring out our happy little marker. That's a bad circle. That's okay. So I think there's a DSP trick I want to show you guys. So remember that thing I told everyone to please write down during 360, where, okay, how do you find the zeros of this function? z3 minus 1 is equal to 0. z3 is equal to 1, which is equal to e to the j, not j0, I think so. Yes, j0. Remember that stuff? And then I think you would have to do, I'm trying to remember this theorem. I'm trying to remember it. It'll come to me. It's like 2 pi f. Yeah, I'll remember it. You remember that thing he wrote on the board, right? Where you have to do this. Z is equal to e to the j. Don't want to say it. Is it 2 pi? There's a 3 somewhere in there. I can't remember. K, something like that? Yes, I think this is right. Oh, yeah, it is K. There you go. Yes, it is K. Okay, because you know why? So if K is an integer, right? And int. Okay, so if K is 0, K can be 0, 1, 2, 3, right? What's 2 pi times 0, right? It's just 0, right? What's e to the j0? 1. All right, what if K is 1? What's 2 pi times 1? 2 pi. What's e to the j2 pi? 1. We're just adding by 1. So that means, you see this right there? Okay, so where's our first 0? So when K is equal to 0, right? Z is equal to e to the j0, which is equal to 1. That's our first 0. Okay, Z1. Now K is equal to 1, right? So that means Z2 is equal to e to the j2 pi over 3. And you know where that is, right? So if we were to make an angle, so here's 0, here's pi, right? Or, yeah, positive pi, right? Here's pi over 2, right? So where's 2 pi over 3? It's like somewhere right here. Okay? And then K equal to 2 is going to be Z3 equal to e to the j 4 pi over 3. Okay? But I don't like writing it like this. I'm a DSP engineer, so we write it like this. E to the minus j 2 pi over 3. All right? We're mirroring it on the other side. So I like going from this side. Does that make sense? So then we're going to get the following. So we just found our 3 zeros. 1, 2, and 3. Okay? And now we just plotted them. Hooray, you're done. So don't forget this. Multiply by 1, force this to 1, e to the j 2 pi k. Memorize this. Okay, memorize. Okay, or if you saw the pattern, how do you divide a circle into 3 parts? 1, 2, 3. How about 4 parts? 1, 2, 3, 4. See the pattern? Or 6. Yes? Poles? Yes, we're about to do the poles right now. So we just did our zeros, right? This is our zeros, right? I'm gonna color code that gray. Okay. Now let's do our zeros. And okay, let's use the purple. Let's color this. Okay. How do you draw that? 1 pole and 2 poles. But how do we represent 2 poles? We just put a 2 there. That's how we do it. Just put an X at the origin and then just write a 2. That's how we determine that. Okay. And now how do we determine this z minus 1? That's easy. That means z's got to equal to 1, which means, aha, wait, let's use the blue one. Oh, look at that. We have a pole 0 cancellation. Okay, so that means if you wanted to make this look cleaner, let's grab the green marker. I like the green marker. And drawing a perfect circle. Close enough. We're going to get the following. 2, 0, 0. And there you go. Final answer. Done. Easy. And so the thing that gets people on the interviews is, okay, they do this, they actually do the zeros, right? But they actually forget the poles. It's this thing that's like kind of pesky. So what I'm going to tell you right now, and it's a good tip to memorize or to think about, is, where did I have that? Remember when I was trying to flip this stuff right here? Like I was like, oh, we have this infinity to minus infinity, right? You see these poles, right? These poles go to like infinity, right? They're going this way, right? Suppose we had a pole on the right hand side, right? And we take it to like super like infinity, right? If we were trying to encompass infinity together, basically the way you model this pole is kind of like this. It doesn't do much. It just changes your phase. It doesn't really affect much, so don't worry about these poles. They kind of don't mean much, but yeah, don't worry too much, okay? So this is what people fail in the interviews. It's really interesting. They're like, okay, draw the poles and zeros. Like you would say, oh, there's like a pole here, right? Okay, the 3 zeros, right? You know how to draw these three zeros, right? 1, 2, 3, right? And you know how to draw this pole, right? Boom. And then they would just have these 2 circles, right? And a pole cancellation, right? But they would forget this. This is what you forget at the end of the interview. Is everyone gonna get that right? Perfect. And now the next thing I asked. What's the next thing I asked? Determine and sketch the frequency response. So we're gonna do this on another sheet of paper. This is important too. So even before talking about it, so one thing I want to tell you is we're gonna try and jump right into it. But remember with the Laplace transform, I was telling everyone, oh, there's a hidden cool domain within the Laplace transform, and that's the Fourier transform. If you were to look purely at this, you get the Fourier transform, right? So same thing with like, oh, we were just wrapping this circle around it. This right here, if you were to run around this circle like this way, you're going to get the Fourier transform for discrete time. Okay? So what we're going to do is if you were to run on this circle, you're going to notice a 0 and a 0 right here when you're walking around it in terms of frequency. Should I show you this? I think I'll show you guys the mathematics before we look at this. So how do you determine a magnitude response? 1 minus z to the minus 3, 1 minus z to the minus 1. So there's one thing everyone here should remember. So how do we transform from the Laplace domain to the Z domain? So there's a little relationship we gotta remember. So it's Z is actually equal to e to the j, let's see, j omega, yes. There we go. E to the j omega, I think so. Let me look at my notes. E to the j omega, I feel like there's something missing. Give me a moment. E to the j omega. Yeah, for our assumption right now, just keep it like that. But if you wanted to do this in terms of sampling, e to the j 2 pi f over f of s is the more technical term. So f is our play variable, as in the Fourier domain, and then f of s is our sampling frequency. But don't worry about this. We're going to deal with this case right now. So we're going to just deal with like DSP numbers. So looking for the magnitude response, actually, something I gotta say. This is correct. Let me see. Because I remember the other thing. It was like z is equal to, it's got to have a real and an imaginary component. And, well, technically, yeah, this has a real and imaginary component if you think about it, right? I'll have to look at back my notes. But point is, if we're going to look at this, I think this is z is equal to e to the s, where s is equal to j omega. I think that's it. The st. Actually, yes, it's this. Oh my gosh, I'm so dumb. So you see this right here, right? Right? Is that what I want to get to? I'm just gonna put a question mark there. Don't worry. This is more like ECG 722, something like that. Don't worry about it too hard. Well, think about it. Think. But point is, let's get to this. Okay. So the thing I'm gonna get everyone is, we're gonna look purely at the imaginary axis. So what we're gonna replace all the z's with is with this e to the j omega. So doing the following: 1 minus e to the minus j omega 3, okay? Divided by 1 minus e to the minus j omega. So there's two ways you can go through this: the painful way or the DSP way. So the painful way would be to take this and convert it to its real and imaginary components. And you can, but it's kind of painful. But there's an easier way, and we do it all the time in 480. It's really, really cool. And actually, not a lot of people do it at all. Like, I'm pretty shocked. So one thing, and I discussed this last time, I think a couple of weeks ago, is you see this frequency, right? We have a 1 minus e to the j omega, right? And this kind of looks like we're going to go into sine. It kind of looks something like a sine, okay? So what I'm going to do is, you see this j omega 3, right? I'm going to divide it in half. I'm going to take half of it away. So what I'm going to do is, let's cut this in half. E to the minus j omega 3, and to cut it in half, divided by 2, okay? So now, what I'm going to have is, I'm going to take a half from this too. E to the positive j omega 3 over 2, okay? Minus e to the minus j omega 3 over 2. All right? Is that cool? So if you multiply this, you get the original thing back. Then I'm going to do the same thing with this guy right here. E to the minus j omega divided by 2, okay? Just taking a half of this little part. E to the positive j omega over 2 minus e to the minus j omega over 2. Is that looking cool? So now, see this? We have a positive frequency, and we have a negative frequency. What does that tell you? You can use that little trick. And because we have a minus sign, 2j, 2j. Okay? What we're going to do is we're going to do some spaghetti stuff. So if we just loop this around like this, all right? And if I were to loop this with that, What are we gonna get? And would it bother anyone if I just combine this already? E to the minus j omega 3 over 2 plus 1 over 2. No. There we go. E to the minus j omega 3 over 2 plus j omega divided by 2, okay? Times, okay, this entire thing times. See this right here? We're going to get the following. Sine omega 3 over 2, okay, for the top part. And then the bottom part, I should probably be using color code. Sine omega over 2. All right, and then making it a little nicer, we're going to get the following. E to the minus, okay, this is minus j omega 3 over 2 plus this is going to give us j omega. And then we're going to get sine omega 3 over 2 sine omega over 2. And then if you wanted to do the magnitude, so if you were to take the entire magnitude of this, so what's the magnitude? Okay, here's a really popular question, and everyone gets this wrong for some reason. What's the magnitude of this? Anyone know? So what happens? Huh? Yes. And then what's the magnitude of this? It's just that. It's just a number, okay? So point is, the magnitude is equal to sine omega 3 over 2 divided by sine omega over 2. Okay? So this right here is actually, I'm going to put it right here, magnitude. And this right here is actually your phase. Cool? So that means your angle is equal to, don't look at the E, just look at this, minus omega. There we go. Which I have to write this on the next piece of paper because I want to show everyone this is really cool. Okay, see that? I'm gonna rewrite this on the next page. I want to make sure this is clear, loud and clear, and hopefully my microphone's loud and clear too. I don't even know if anyone's in the class, virtual class. Anyone's here? Oh, we have one person. Oh, we do. Should I keep recording these Zoom lectures? Yes. Yeah. Or, well, not the Zoom lectures. I'm still going to do the recordings, but should I keep the Zooms? Actually, yeah, you're not wrong there. Okay, yeah, I will. Page 5. Okay, so rewriting this, we're going to get the magnitude. And there's another format where I'm going to write it. So if you guys were kind of alluding to what I was trying to do, omega, actually I'm going to, let's put it right there. Omega is equal to 2 pi f, but in terms of sampling, we're going to do f of s, okay? Don't worry about this f of s. Just think of it like some arbitrary number. I'm going to do something cool after this. So 2 pi f, but divided by f of s, okay? Don't worry about it, all right? So I'm going to try and replace all this omegas with this to make it more friendly. Sine of 2 pi f over f of s times 3 over 2 divided by sine 2 pi f over f of s times 1 over 2. And then this should give us the following. Sine of, hold up, 3 pi f over f of s, sine of pi f over f of s. Is that making sense now? So now we have something in the Fourier domain. Now we can actually see this. So if you wanted to, what's the value at DC? So if you wanted to know, okay, actually now this right here becomes h of f, okay? So if f is equal to 0, so we're at DC, okay? We're looking at like a DC frequency response. Since this, if we put a 0 here, that just makes a 0 divided by 0, right? Then we're going to have some weird case where, oh, we just can't do anything. So now we got to do that weird, I think it's like L'Hopital's rule, where we take a derivative of this, d of df of that entire thing, which is equal to, if we were to take a derivative of this, we're going to get, okay, 3 pi over f of s cosine of 3 pi f over f of s divided by pi, let me see, hold up, pi f of s cosine of pi f of s. All right, and now if we punch in 0 into this and into this, then we're going to get the following. So this cancels out, that cancels out, that cancels out. We're going to get 3 times cosine of 0, that's 1. Easy, done. And now if you wanted to get power, right? DC power, all we do is just 20 log 10 of 3, and that is equal to, does anyone know that on the top of their head? I'm going to use MATLAB. Oh, look at that. I got some surprises for you too. Hold up. Okay. 20 times log 10 of 3. 9.5. And there we go. dB. Pretty cool, right? And then we're gonna do the phase. I forgot to mention the phase. H of f. There we go. We kind of labeled it as like this negative omega. I think we did. Yes, we did. All right. So we're gonna get the following: minus 2 pi f over f of s. Does that make sense? So what this is basically telling us is, if we wanted to rewrite this more family friendly, let's make it some constant. This is linear phase. When you have f to the power of 1, it's constant, it's linear. That means this system that we have designed right here will have linear phase, and this is really good. So what I'm going to tell you is, okay, if we wanted to draw this frequency response, and I think I will tell you a sketch. Oh yeah, we have to sketch this. I will sketch this for you. Don't worry, I brought a lot of paper today. Okay, so sketching this magnitude response, function of f. So what you're going to see is the following. So what I'm going to try and tell everyone right now is, with this circle right here, this right here is 0. And okay, we're going to do it this type of way. So we're going to use f of s. So there's one thing I'm going to try and tell everyone, and this is like DSP, is when we're sampling something, we have a thing where we have 0, f of s, which is the sampling frequency. And then we have this thing called f of s over 2, which is called the Nyquist frequency. Okay, so don't worry too much about this right now. What I want to try and tell you is, if we wanted to map this Fourier domain into this would be 0, this would be f of s over 2. I mean, no, 4. This would be f of s over 2, 3 f of s over 2. And then this would be, wait, no, hold up. F of 4, f of 2, half. This would be half, 4, and then this would be f of s. Okay, so this is 0 to f of s. Okay, So what we're going to see in our magnitude response, if this was f of s, okay, is let's divide this circle into thirds. So if we divide it right here and right here, right, we're going to get this point where we have like zeros. So if we were to look at this right here and this right here, this would be f of s divided by 2 pi f of s over, no, over 3. Yeah, that one, 2 f of s over 3. Don't worry too hard about this, but we're gonna, if we divided this circle into thirds, okay, 1, 2, 3, right, we're gonna get the following. So here we have our DC, right, and we just confirmed that our DC right here is like 9.5 dB, okay? And if we were to go around the circle, you're gonna see the following. You're gonna see something like this. And then you're gonna see something like this where it forces to 0. And if we were to come back on our own, we're gonna see something like this. So this is what we're gonna see, okay? And then this is h of z, the magnitude response in dB. So that means if we were to do the phase, I know this is like a lot off a topic, but this is really, really cool. I'll show you guys later. If we wanted to do the phase, and the phase is defined right here, right? What's our phase when f is equal to 0? It's just 0, right? So we're gonna start here, 0 degrees, okay? But what I'm gonna try and tell everyone is, how do I want to say this? See, this is minus 2 pi f over f of s, right? How do we, so if our frequency is equal to, if f is equal to, how do I explain this? F of s, okay? So that means we cancel this right here, right? We're gonna be at minus 2 pi. But minus 2 pi is also 180, right? So that means if we're here, right, we somehow are going to be at minus 180, okay? Simple? So what I'm going to tell everyone is, have you ever seen LT Spice do something weird? When it gets to 0, and I'm going to draw the following, and it's going to look cool. So this right here is going to do the following, and we're going to do this. This is going to jump by minus 180 degrees. There we go. And then we're going to do this pattern again. Oh. And I think that's right. I think that's how you do it. Oh, yeah, this is correct. There you go. Something like that. You're going to see something like this. Okay? Does that make sense? And then this slope right here is going to be your minus 2 pi f over f of s. Okay? It's linear. So I know this is like a lot off topic. This is more like a mixed signal circuit design, but this is like introduction to that. So that I'm going to tell you, like, this stuff is really practical, and I'll show you guys an example. You want to see the MATLAB first, or you want to see the LT Spice first? Oh, look at that. How'd I do that? So there's a cool way to model stuff online or on LT Spice. And I'll put myself right there. So the way you model, actually, even before that, I will show you one thing before we get to how did I even design that. So the final thing I asked was, how do you determine the block diagram for this? So block diagram. Okay, so this right here are zeros, right? And these are our poles, okay? Let me try to see if I can show it to you. Remember how h of z is equal to y of z divided by x of z, right? This is equal to 1 minus z to the minus 3 divided by 1 minus z to the minus 1, right? So then if we multiply this to this and this to that, right, we're going to get the following. Y of z minus y of z to the minus 3, right, is equal to x of z minus x of z to the minus 3, right? And if we were to turn this back into the inverse z transform, you're going to get the following. Y of n minus y of n minus 3 is equal to...
I think that's y to the n minus 1.
Huh?
1 instead of 3.
Oh, 1. Yeah, sorry. Thank you. 1. Okay, thank you. X z minus x of n minus 3. There you go. Oof. Done. All right. And you know how to draw these delays, right? Easy, right? So what I'm going to show you is, if we were to draw a node C of n, right? So here's x of n, right? So C of n, if we were to draw something like C of n, if we were to model this into one node, what does C of n see? It sees the direct input, right? Right? But then it also sees a delay. And I'm going to do it like this. Z to the minus 3. Does that bother anyone? Nope. And because it's minus, plus. Cool? And now if we wanted to do these poles, right? You know, if we try to put this, okay, if we wanted the output, right? I'll do it right here. Y of n is equal to C of n plus y of n minus 1, right? So what does the output see? It sees a positive, right? So that means if we were to do the following, y of n, and to feed this back to a z to the minus 1, right? This right here has to be a positive. Make sense? And then that's our full block diagram. And now you can put this in LT-Spice. And I'll show you. So that means we have x of n, the input which is feeding into some adder and some delay. And then we have something going back and adding on itself. And I'll show you this. It's really cool.
Hey, Dave, what's that thing called?
Which one?
That.
That's a transmission line. So there's no way of modeling delays in like these wires. So to model them, you use this transmission line. And the transmission line, you can basically say if the signal goes in, delay the signal that's here, if you have a sine wave, by this many seconds. And then this right here is a characteristic impedance, which to summarize 430 in a nutshell, is a special thing for matching. So anytime you see this Z not equal to 50, that's 50 ohms is a characteristic. All wires have, wires that we kind of use in the lab are 50 ohms. And that's why I have to put this 50 ohm in terminal right there too. For matching conditions. Don't worry too hard about that. But point is, this is supposed to model delay. All right? So here's our input, Vn. Okay? And it goes into this adder. It's going to add, right? And then our little hand calcs say, okay, we need to have 3 delays, right? And then we have to subtract it. So what I did is the following. Let me see. So I picked 30. So I think the sampling frequency for this that we have is going to be, I think, 100 megahertz. Don't worry too hard about that. Just treat this as like 3 delays. So how do I want to say this? Each z to the minus 1, what I'm defining in my LT-Spice, I don't want to get too deep into this. Oh god, yeah, I don't want to get too deep. I'm going to treat z to the minus 1 is equal to like 10 nanoseconds, okay? Don't worry too hard about that. Okay? So we have 3 delays in here. Then we add them and we get some output, C of n, okay? Then here's your output, right? And there's no way of making this a plus. So to make it a plus, I just kind of added this again. And then I have one delay right here, right? So that's how I'm modeling an LT-Spice. It's kind of really weird. But this is like your cheat way of how to like simulate digital circuits in LT Spice using analog models. So if we were to run this, you get the following. And oh, what's that value that we have right there? That looks like 9.5. Did we do it right? Actually, okay, because someone has OCPD. Boom. 9.5. Cool. Aha. See? Easy, right? And here's our little phase. And then you see how it's going from 0 and then jumps like this and jumps like that? Why does it jump? So if you didn't include these absolute values, you're actually going to see something like this. You're going to see a sync function. And how do you model negative numbers? By adding a phase. So in this case, we're adding 180. Okay? And to prove that, there you go. Let me get your phase. See that? When we get to that little discontinuity, we add phase, and now we're there. And then we add phase again, and boom, we're up there. And what number did we end at? Oh yeah, 0 degrees. Did we do it right? So this is how you would implement digital signals and like get actual numbers from them. So this stuff is like actually real. It's not all like toys and stuff. Want to learn more of this? 722. Take that class. Really fun. Dr. Vicker will teach you signals and systems. I will trust you. Now, how about we prove this in MATLAB? And let's look at an assignment. You guys like assignments? Let me see. Which one is it? Is it this one? Oh, no, that's the other surprise I have for you. Quiz 10, problem 1. Oh, you see that computer assignment? Should I click on that? Nah, I'm good. So, how do we model this in the Z domain? So, how do we do that is, remember in the Laplace transform, we did like this mesh grid stuff? You just do all the same thing. Same thing, right? Just model your numbers. And here's our transfer function that I've already pre-coded into our system. So just model it like this. Okay, so write your Z, right? And then make it Z to the minus 3, Z to the minus 1, right? And then you get your transfer function. Easy, right? Get your power. And then I'm going to show you something cool. So I drew a circle, and I will show you that right here. Look at that. So this circuit that I have right here, or not circuit, actually, yeah, this circuit right here, modeling it like this, remember how we were saying, oh, this is what it's going to look like? Prove it in MATLAB. Can you prove it in MATLAB? Does that look like it? We have 2 zeros and 2 poles, and we have nothing at DC. 2 zeros, 1 0 here, 1 0 there, 2 poles, and nothing there. And then this black line that I drew there is just the unit circle to help you see it. Cool? Now I'm going to show you one more trick. And I think we're going to have to do the second half of the quiz probably next class, but maybe I'll make it even more cooler or something like that. So I modeled this the Fourier transform. So remember that one? Okay, because someone's probably saying, David, we're not doing anything in this class. I will show you. EE360. Homework assignments. Oh, what's that? I'll have to figure out the date on that assignment due date. Don't worry about it. Let's go to this. Oh, look at that. Hand calculations determine a system function. See, we're actually doing stuff. Find the poles, find the zeros, calculate H of Z using MATLAB, using the freaks with a Z at the end. Calculate the frequency response. So the Fourier response, or Fourier discrete time Fourier transform. Okay, and we're gonna do the following. Okay. So when you're modeling your numbers, since we have a third order system, we need to have at least 4 coefficients. So for our numerator, it's 1, 2, 3, 4. This right here is the 1. Here's z to the minus 1, z to the minus 2, and z to the minus 3. Okay? This is z to the minus 0, z to the minus 1, and then there's no other powers there. Okay? And then here's using the free FREQZ. Here's this. And then I will show you this. And boom. And look at that purple line or magenta line. That right there is the Fourier, discrete time Fourier transform. Pretty cool, right? And what's that? That's DC. And what's our DC value? 9.5. Really, really cool. Sweet. So now, and then yeah, that's what I did right here too. If you didn't want to see it on a graph, you can see it as a 2D figure. And hey, does that look like something that we did in LT Spice? Is this cool? Are you understanding this? And look at that zigzag. The reason why I'm doing these practical problems and not the assignment is because you guys are looking at the assignment and you're like, oh, I don't know what the hell is this going on. We're doing these hand calcs to prove this in LT Spice and in MATLAB. And if you wanted to make your own systems in LT Spice, go ahead. Now you kind of can monkey around with that or take 722. But now you can say, oh, I have 2 systems, LT Spice and MATLAB, that are verifying our hand calcs. We're doing this. It's making sense. And then you're like, okay, David, oh, well, oof, I didn't erase that 4. Roots. How do we prove the roots of the system? The zeros and the poles. And I did this just in case someone's going to copy paste. Someone's kind of doing it. And oh, what's that? Look at that. And then look, here's your zeros, right? Here's your poles, right? We have 3 zeros, right? We have 3 poles, right? And here's the location of the zeros. The zeros are located at this, this, and this, right? Does that look something cool, right? And here's the poles. We have a double pole. Remember that double pole from this double pole, right? And then we have 2 zeros, but we have a third 0 and a third pole that are canceling out. They're gone. And that is this right here. You see that 1 right there? This and this cancel each other out. So I could have written here, note, oh, there's a cancellation here with Z3 and P3. Cool, right? And then you can take these zeros and turn them back into its like equivalent, what do you call it? Transfer function. And then I did this. Here's Z1 minus Z to the minus 3. And then 1 minus Z to the minus 1. Is that really cool? And now someone's saying, David, I still can't see this. Okay, you're going to see this now. There's a thing called the Z-plane. And you can do this in the Z-plane. Is that enough proof for you guys? Look, x2. Here's a 0 there. Where is it located? -5 and that J value. And there you go. And then, oh, look, you see that right there? That's a 0. You can't even, whatever. It's not doing what I want it to do. Pole and a 0 at the same point. Is this making sense? Do you now know what to look for in this assignment? Okay? The reason why I'm doing this is, well, hopefully the ones who are understanding the tools I'm giving them will change the numbers in a way. And hopefully the ones who I've caught on the last assignment do the assignment. So does that make sense? And then I would assume everyone knows how to do the residues function and everyone knows how to do conv, right? What value does the system settle to for, I think, the step response? And do I do a hand calc on that? Here's a hint. I'll probably show you this on this piece of paper. What page is this? 6. Do I want to do? Okay, whatever. let's do it here. And I think this is probably the last thing I can talk about. I didn't get to the second part of the quiz. We'll probably talk about that at a later time. 7. Okay, so suppose you had the following function, like 1 minus z to the minus 2, 1 minus z to the minus 1, right? Something like that. And this is equal to h of z, right? Okay, so you know that y of z is equal to h of z, x of z, right? But if x of n is equal to u of n, right? What's the z transform? Right? Easy, right? And where's the poles and zeros for this? You have a hidden 0 there. Ooh, tricky. So that means this one's going to look like this. You have a 0 right there, and then you have a pole right at DC. Cool, right? That's a step response. So then how do you do this? 1 minus z to the minus 2, 1 minus z to the minus 1, 1 minus z to the minus 1. How do you do this? You just the values. I'm going to call this one den 1, den 2. See that? You guys can probably figure that out. And then you can treat it the same way with the residues function. And let me show you the code for that one. How do you do the residues function? And I give everyone a code if you're reading this. Look how many poles you have. Here's 1, here's 2. You have 2 poles, right? So if you have a second order system, you're going to have 2 poles. So that's the little hint. Actually, I think you can probably just copy this and you're done. For the impulse response, for the step response, no. You're going to have 3 poles. Okay, so I'm going to do something cool. I'm going to have to do something quick. Someone's going to screw this up. Suppose this is a second order equation, right? Second order equation, right? So if we were to do, or actually, let's just change it like that. And let's make this 3, whatever, okay? So if this is second order, right? This is going to have 2 poles. Okay? So that means if you were to do the residue or the inverse Laplace transform, you're going to have res 1 p1 n u of n, right? Plus res 2 p2 of n u of n, right? For a second order equation, okay? For this one, this is a third order. So that means if you were to do some h of t, right? Or h of n, right? It's not going to be this. It's going to be this. Res 1 p1 n plus r2 p2 n. But you have a third pole. And that's your general equation. Okay? That should help you out. And now I think you guys are able to finish the first half of the assignment due whenever you guys want. Never. That'd be great. I'll think about it. But yeah, gee, I didn't get to what I wanted to. But I will upload this to hopefully help out with anyone who wants to like tinker with it and have fun. We will probably go over the second half, or should we not? Like I made this a 2-parter quiz, and I gave everyone this. Tricky. Huh? Should we go over it now, or should we go over it another day? All right. Yeah, I'm getting tired too. I told you this is gonna be a big quiz. Or should I just make this one 10 and then this one 11? All right, yeah, you see, I've never done this. I was like, I did this as page 1 and page 2. I was like, this is going to trigger my OCPD. So, yeah, I'm going to make this 11. Okay, we'll have 2 more quizzes, all right. Is there any other questions regarding the first half of the assignment or anything about what I've discussed today? Okay, everyone can figure out magnitude responses, draw poles, draw the region of convergences and stuff, like stuff like this, and do inverse Laplace transforms. Next class, we're gonna go over, because I want to get the state space equations pretty soon. I think we have to have that exam after the break. Yes? Oh, there is a comment. Thanks. Oh, thank you. Yeah, I think we're gonna have to make the exam over the after the break. I might have to do a video on maybe Monday, or you guys want to do a Monday video or something like that? What time? 5 o'clock at night or 11:30? I can do 11:30. Oh, you guys have Dr. Shill stuff though, right? Or should I just? Okay, I'll try to do 5:30. We'll make sure you guys get your money's worth. All right, everyone, have a good day.